Alright, so in the time we've got left here, what I want to talk about here is just solving the equations. We've done a little bit of this, like in each part as we looked at exponentials and then as we looked at logarithms, but I want to address these specifically here and give you a little bit of strategy for some of these. So I want to start with exponential equations, and there's three kind of cases that we can look at here. The first of these is a little bit obvious if you think about it, but I also want to show you the algebra of why this works. The first case is when the exponentials are on both sides of the equations and the bases are equal, okay? So here we have e to the 2x and e to the x squared minus 8. All right? Now, if these two are equal, someone think about this equation. How would I figure this out?
Could you just drop the e?
You just do 2x is equal to x squared minus 2.
Yeah. 2x equals x squared minus 8. Because if I'm raising e to powers and I know it's equal, then those powers must be the same. Even though they look different, the value of x is going to make them the same. And now I just have a quadratic equation that I'm solving. So 0 is x squared minus 2x minus 8. That factors into x minus 4, good, and x plus 2. So x is 4 or negative 2. Okay?
But do you have to do, can it not be negative 2 in the domain?
Well, that's where we have to think here, okay? What's the domain of an exponential function?
It's 0 or not 0. It's greater than 0.
It's like,
Let's think about it. What does the graph look like? Do you remember?
like that.
That's logarithmic.
It's not touching the
Oh,
zero.
it's like this.
It's like
An exponential function?
An exponential.
It's a parabola.
Isn't it a
Not a
parabola?
parabola.
No.
Quadratic.
It's,
Oh,
it's
yeah,
cubic.
my
Isn't
bad.
it like a cubic that's kind of
It's a horizontal.
curved?
Parabola side. No, it's that.
It
I
looks
just
like a
said
kind of thing
that.
that does the
It
thing.
looks like that. Okay.
It's not
There's our domain. There's our graph for
negative infinity.
the exponential, okay? Actually, I'm sorry. That would be an exponential with a negative exponent. Let me give you an exponential with a positive exponent. There we go. Either way, though, what's our domain?
Negative infinity, positive infinity.
Yeah, x is any real number, okay? Because think about it, x is your exponent, right? On an exponential, x is the exponent, so you can raise a number to whatever number you want, okay? We can raise a number to a negative number or 0 or a positive number, okay? So the domain issue is not going to be very much of an issue when we're dealing with exponential equations, okay? Now, just so you can see here, the algebra that's taking place is this. Because the base is e, I could take a log with a base of e on both sides. What do we call that?
Natural log.
The natural log. If I took the natural log of e to the 2x and the natural log of e to the x squared minus 8, remember the exponential that has the same base as a logarithm is the inverse. Okay? Yes?
Can you just remind me what E is again?
E,
2.7 above the.
yeah, E is 2.718 and so on. It's actually defined as the limit as x approaches infinity of 1 plus 1 over x to the x power. Okay, you don't need to know the definition, but that's what it is. Okay,
Isn't the equation that you wrote with the natural log just the same thing?
well it is. We just took the ln of both sides, and that's the algebra behind what we did logically.
Yeah. Yeah.
Okay, so I just wanted you to see that.
But
So-
if it had the log there, would you have to take into consideration the domain differently?
If it already had the logarithm in the original, then yes, we would have to consider the domain.
Wait, so if it has the same base, that means the exponents
That
are
mean-
equal to each other.
Well, if it has the same base, then the exponents are going to be equal to each other. Okay? So, what happens if only one side has an exponential? Okay, like this. Well, the first thing that we need to do is get that exponential portion, in this case, the 6 to the 5x, all by itself. All right? So I'm going to subtract 5. And I now have 6 to the 5x equals 1296. Okay? 1296. And now, there are kind of two ways that you might do this. One way is to just take the log of both sides. Okay? Log base 10 of both sides, the common log. Alright, you may have learned that. But in doing that, you end up re-deriving the change of base formula that we learned. And we don't want to do the same work over and over and over and over again. Okay? So to cut out a step in our process, what we're going to do is instead use a logarithm that has the same base. So here the base is 6. We're going to use the log base 6 of both sides. Okay? So that's what we're doing.
So then it's just 5x is equal to log base 6 of 1296.
That's right, okay? 5x equals whatever that is. And here's where the change of base formula comes in. Remember, our calculators, most of our calculators can't do a log with a base of 6. Okay? So, our calculators can do a log with a base of 10 or a log with a base of e, usually. We usually have those two buttons on the calculator. So, we use log of the original argument. Notice I'm changing the base from 6 to 10. But to do that, I have to divide by the log of the original base. So the base goes in the bottom. Okay? Good.
If we do have a calculator that can do it, can we use it?
In your work, yes. But if I ask you to show me a change of base formula, you should know how to do it. Okay. So you punch that into your calculator and you get 4. Okay? Be careful with parentheses. When you hit the log button on your calculator, it's going to put an open parentheses. So if you put 1296 divided by and don't close the parentheses, it's going to mess you up. Okay? So here x is 4/5. Okay? Any questions? Yes.
You just cross out the logs, right?
You're not crossing out the logs, you're actually evaluating. Okay? Alright, so finally, we have this third case, which is a little bit more challenging to deal with, but you actually have two different ways that you can handle it. And you should know both ways, because the one way is faster, but it doesn't always work. Okay? And by it doesn't always work, it's not that you do it and you end up with the wrong answer, it's that you literally cannot do it. Okay, so don't worry, oh wait, is it going to work this time? You'll be able to see. Okay? Now, here we have exponentials on both sides, but the bases are different. Okay? One option that I have is I can simply take the log. Notice I'm using a base of 10 since I have different bases here. The log base 10 of 2 to the 4x and the log base 10 of 8 to the x plus 4. Okay? And you'll notice what's going to happen here is Now that I have it inside a logarithm, I can do something with those exponents. What can I do with them?
Bring them in front of the logarithmic.
That's right, I can pull those out in front. So now it's 4x times the log of 2 equal to x plus 4 times the log of 8. Now, I don't expect you to know what the log of 2 is, all right? But you can use your calculator now to solve it, okay? If you do log of 2 and log of 8 on your calculator, yeah, you're going to get decimals, but that's okay, all right? Does that make sense? Okay, now I'm not going to finish solving it because we need the calculator here to do it. But that is one way you could do it. And the nice thing is that works whether it's 2 and 8 or 2 and 7 or 2 and 11, it doesn't matter. The reason why we have a simpler option when it's 2 and 8 is that 8 can be written as a power of 2. Okay? The second option here would be to rewrite 8 as 2 cubed. Okay? Now, obviously, this is what I said by this method is not going to always work. If it were 2 and 7, I can't write 7 as 2 to a power. It just doesn't work. Okay? So, how would I simplify that 2 cubed to the x plus 4 power?
2 to the 3x plus 12.
Very good. You multiply your exponents together, and we've got that. And now we're back to that first case where our bases are the same, so therefore the exponents must be the same. And you get x equal to 12. Okay? Now, we would have gotten the same answer doing it the previous way, and there are some times when we just have to do it the previous way, but this is a nice method to use if you can. Okay? Questions? All right. Now, here's another example of a variation of an exponential function. It's known as a logistic function, as we'll see later, but it's the same principle here. We have an exponential portion of the equation that we need to isolate first before we can take a logarithm of both sides. So let's do that here. We're going to multiply both sides by this 1 plus e to the negative x. So we have 525 equals 275 times 1 plus e to the negative x. Then we're going to divide by 275, which actually ends up equaling 2. So 2 equals 1 plus e to the negative x. We still don't have the exponential part isolated, but if we subtract 1, we will. So e to the negative x equals 1. So now, since it's e, we're going to take the natural log, because that's a log base e, of both sides. That will in turn undo the exponential, leaving us just with negative x equals the natural log of 1, which, if you think about it, e to what power equals 1? That's 0. Okay? We're thinking about ln of 1, so e to what power equals 1? That's e to the 0 power equals 1, so that's why ln of 1 is 0. In fact, the log base anything of 1 is going to be 0. So since negative x equals 0, of course x equals 0 as well. Alright, and that's the solution to our equation. When we're dealing with logarithms, we also have 3 cases, and these cases are actually very similar to the cases we had with exponentials. First of all, if we have a logarithm on both sides that have the same base, okay, we can simply say that the arguments must be equal. Okay? So in this case, 4 plus x must equal 2x minus 1. Because we're taking the log base 9 of both of them and we're saying that they're equal. Okay? So that means x must equal 5. Now, one thing I will say when we're dealing with logarithmic equations is that we do have to be careful with our domain. What is the domain of the logarithmic parent function?
Log base 10 back. Oh, the domain of the parent function.
Yeah, what can x be?
0. Greater than 0.
X has to be greater than 0. There we go. Your argument has to be greater than 0. So in this case here, I know that 4 plus x has to be greater than 0. And I also know that 2x minus 1 has to be greater than 0. Alright, so x has to be greater than negative 4. And x has to be greater than 1/2. Okay?
Why can't you just find 5 and then ask if 5 is greater than 0?
Well, that's what you can do. If we took 5, 4 plus 5 is 9, that's greater than 0. 2 times 5 is 10, minus 1 is 9, that's greater than 0, so that works.
But do you have to plug it in, or can you just say, oh, 5 is greater than 0, so I'm good?
Well, that's the thing. You have to look at the domain of the log function you're working with. Because notice here, the log on the left here has a domain of x is greater than negative 4. The log on the right has a domain x is greater than 1/2. So you have to take the more restrictive one of those, which would be x is greater than 1/2. That would be the domain of x in this equation. Okay? So if I got, 0.2, that's smaller than 1/2, that's going to mean one of my logs is going to be negative. So I'm not allowed, x cannot be that. Okay?
You always take the bigger one?
Yes. It's kind of like with the radical. The domain was greater than or equal to 0, but if you had radical x plus 5, then x just had to be greater than or equal to negative 5.
Okay.
It's a similar idea there. Now, our second case here is when we have an exponential only on one side, and this is where, similar to when we had, a log on only one side, it's similar to when we had an exponential on one side. When you had an exponential, you rewrote it as a logarithmic equation. Here, we're going to rewrite it as an exponential. So what's the base of our exponential? 10.
Oh, 10.
To what power?
6.
To the 6th power equals
X squared.
x squared. And then you can square root, and x is 10 to the 3rd. Okay? And then one last one real quick here. If we have multiple logarithms, this is where we have to use those properties of logs. We're going to get the logs on one side, so we're going to subtract ln of 2x plus 1 minus ln of x equals 3. And then when you have subtraction of logs, what does that mean? Division. Okay? Division. So it's going to be ln of 2x plus 1 over x equals 3. Now we're back to the previous thing where we have a single logarithm. We can rewrite it as an exponential. Okay? So it would be e to the 3rd, because e is our base, equals 2x plus 1 over x. And this one will get a little ugly, but it's not.
Wait, what is
Terrible.
Wait, what is your base?
This is a log base e, right?
Okay.
Oh,
So when I rewrite it as an exponential, I have to have
Wait, how did you?
a base of e.
figure out that it's
Oh,
log
he's just
base?
writing it as an exponential.
Natural log is always, okay?
because you know when you're writing it as an exponential, you take the base of the function, and the base in this case is e.
Okay? So those are your basic strategies for exponentials and logarithms. Not terribly difficult, but it does need some practice, okay? So work on the practice. If you're behind in your IP, get caught up quickly, okay? All right, we'll see you guys later.